Now we're going to try to explain how the new modeling came about that fitted the Wheaton data better. So on slide 8 we have the outline showing that we're going to draw on modeling ideas from multi-level factor analysis. On slide 9 then you have a model, a vector of observations or variables y for individual I in cluster J, decomposed into an intercept or a fixed effect and 2 random effects, that is 2 latent variables, one on between varying across the clusters J and one on within varying across individuals within cluster J. And this is the regular random effects ANOVA decompositions, these 2 parts being independent. And for each of these B and W components we assume a factor structure with a factor loading matrix lambda and a factor vector F and the residual vector epsilon, both for between and for within. And that gives us a covariance structure for the observed y vector, which is the sum of the between and the within covariance matrices. And each covariance matrix then has a factor model structure of the standard kind, lambda, psi, lambda prime plus theta, where psi is the covariance matrix for the factors and theta is covariance matrix for the residuals. This seems to have started, this interest in multi-level factor analysis, with an article by Lee Cronbach, or a research paper rather, in 1976, where he did research on classrooms and schools, and that is clearly hierarchical data, students within classrooms and students within schools. And in 1978, or actually earlier than that, Kjell Härnqvist from Sweden came over and visited Cronbach at Stanford and got inspired, went home to Sweden and wrote this paper, Primary Mental Abilities of Collective and Individual Levels. Now, at that point, the estimation of the model was quite rudimentary. For instance, to get the between matrix estimated sigma b, they simply created a covariance matrix, a sample covariance matrix, that started with the means in each school, the observed means, so y bar in each school, and did a covariance matrix for that. It's not quite right, but it gets close to what you would get if you do a more efficient estimation. And then later on, Harvey Goldstein and Rod MacDonald started working together on the general model for the analysis of multi-level data. They had a psychometric article, and then another MacDonald and Goldstein article in British Journal of Mathematical and Statistical Psychology, focused on how you would express the likelihood for maximum likelihood estimation. And I took an interest in this when I read those articles. I was inspired by notes from Rod MacDonald, quite detailed notes. So in 1989, I wrote a paper, an overview paper, part of which dealt with multi-level factor analysis estimation, because at that point there wasn't a general computer software program to actually do the analysis. And playing around with the formulas, I noticed that you could use multiple group SEM analysis using, say, Lisrel. And in the case of all clusters having the same number of individuals in them, you could actually get maximum likelihood estimates out of it. The group would be, it would be a 2-group analysis, one for analyzing the between level part and one for analyzing the within level part. And in 1991, I looked at various kinds of applications of that in analysis of class and student achievement components. And then I wrote an overview paper that dealt more specifically with how you would go about the analysis, the multi-level analysis, which steps you would take. And I focused very much on students within classrooms or schools and achievement testing. And it's clear then that there are typically fewer between-level factors FB than within-level factors FW. And the FB interpretation is quite different from the FW interpretation. So for instance, on the within level, you may measure a student's math and reading skills and come up with, say, 2 factors that are correlated. But on the school level, these measures are more influenced by general school excellence. So a single factor on between and 2 factors on within. Now, if you take a look at this factor model in more detail, we can write it assuming that we have only 1 factor on each level. So instead of a matrix lambda, we have a vector, and we have only 1 factor, single factor here. Same thing on the within level, single factor on within. So if you look at this expression, you can actually write it in a different way, in a 2-level fashion. So on level 1, you can write it as y equals an intercept nu that varies across clusters, plus the within part, factor structure on the within part. And then you can say that nu, this random intercept, has an overall mean and a variation across that mean that is the between part. Now if you insert this nu j expression into equation 1, you get the expression that we have at the top. But by writing it in this fashion, as those 2 equations, it becomes clear that we're dealing with a random intercept here. You know, whatever is random has a subscript j on the right-hand side. Lambda doesn't have that in this application, but you could. But the intercept has it. So it would correspond to item bias or differential item functioning if you talk about measurement invariance matters. So 2 key aspects. 2-level factor analysis can be viewed as a random intercept model where the intercepts have a factor structure. You don't have to have a factor structure. You can have just totally freely correlated intercepts if you want to. But very often you can reduce the dimensionality into 1 or a few factors. Now, because the random intercepts appear for the factor indicators in this equation, we allow for a certain form of measurement non-invariance. That is, y as a function of the factor differs for students in different schools j. So there is something about the school context that makes your achievement score, for instance, lower or higher. So the measurement model is not the same for all students in the whole sample. So that's a form of allowing for measurement non-invariance. Doesn't mean that we have to throw out items that have bias, but it just means that if we have to model it, we have to represent it. Turning then to slide 12, I repeat these 2 equations, the level 1 equation here and the level 2 equation, and try to show this in diagram form because it's easier to talk about general modeling and relationships between models through diagrams than formulas sometimes. So we have here on the within level, that's level 1, we have y expressed as this right-hand side. So we have the observed y's, and the random intercept is marked by a filled circle here, the intercept in the measurement equation. And then the lambda w's are loadings on these paths. And we have fw here, and the short arrows here correspond to epsilon within. And then these filled circles, marking the fact that we have a random intercept, become open circles, that is, continuous latent variables on the between level, that is level 2, that is nu j is equal to nu plus lambda b fb plus epsilon b. So here we have the fb, lambda b loadings and epsilon b, and here nu 1, nu 2, nu 3 are the 3 different random intercepts. And in covariance structure then on within is sigma w, that's the variances and covariances among the part of the model that is represented by these 2 terms. And sigma between represents the covariances on these variables, these three variables, which is represented by these two terms. On slide 13, we will be going deeper into multi-level factor analysis and take a close look at the covariance structure for students within schools. And we're going to show the data in a different fashion, showing the data for each student. This is a way of displaying the model that's often used in statistics and in econometrics. So as a simple example, we have School 1 and School 2, and we consider 3 students in School 1 and 2 students in School 2. Each student has then a data vector y that contains the 3 variables that we talked about on the previous slide. 3 variables here, 3 here, etc. down. So considering the first student here then, the covariance structure for that student is the sigma w plus sigma b that we've talked about. The sigma w coming from the within level part of the factor model, and sigma b coming from the between level part of the factor model. And every student has that diagonal element, sigma w plus sigma b, all the way down here. And that's because we assume that the students come from the same population. Now down here we have zeros because students of School 2 are uncorrelated with students in School 1. And that's because we do random sampling of the schools. So we have independent observations across schools. Now within a school, you have a covariance between each student, that is sigma b, and that is a non-zero element. And there it comes about because they share the same school. This is the same for students in the same school. So we get a sigma b contribution here in the off diagonal. And that's what creates the interclass correlation. It's the numerator of that interclass correlation. So we have 3 of those sigma b's for those 3 students and 1 for these 2 students. And in statistics or econometrics, this is usually expressed with help of matrix algebra Kronecker products. Now, what does this model mean then, and how should we look at it? Well, it's interesting. We can show it in a very simple fashion in the model diagram on slide 14. So here we consider the simpler case of 2 students for each of the schools. So here is student 1 and here is student 2. So we have sigma w for each of the students, same sigma w, and we have sigma b that the students have in common. So the observations on these 3 variables and these 3 variables are correlated because they're influenced by the same school random intercepts. The random intercept for the first variable influences y11 and y21 with coefficient 1. So all of these variables correlate because they share the same school. Now, of course, we could have a more general model. You could, for instance, consider in small group research a leader and a follower and have an arrow from student 1 to student 2. That is a correlation between the students beyond the correlation that comes from their common influence from the school random intercepts. Now, what are we looking at here then? We have quietly made a paradigm shift because how would you analyze this? And what is the model? Well, the model is the same as what we talked about on slide 12. It's this multi-level model, just shown in a different way. And it's different because we would not analyze this by 2-level analysis. We would analyze this by single-level analysis in wide format. Wide format because we have not only 3 variables, but we actually have 6 variables. 3 for each of the students. So it's a wide format analysis that estimates the same model parameters as the 2-level model and 2-level analysis. Now, typically you would not do 2-level analysis in a wide format, certainly not with many students per school. Say that you have 10 students, then you would have 6 times 10, 60 variables to contend with. So that's not practical. And that's why you benefit from two-level analysis. But there are cases where you have relatively few members of each cluster. So here we're talking about cross-sectional analysis, students within schools. But what about longitudinal analysis, where you also have time points, where you also have a nestedness, that is time points nested within individuals? And there you would have relatively few members per each cluster. This would be 2 time points. It wouldn't be too hard to expand this to 3 time points or 4 time points. And then you end up with a single level wide analysis of longitudinal data. And here you have the model on slide 15. Now we have t equals 2. That is time point 1, time point 2. It's the same individual at the 2 time points. And the reason the variables correlate across time is because they share the same individual random intercept for each of the items. So that creates the correlation across time that we want. And that's been brought up. That idea has been written about by Hamaker in a 2016 multivariate behavior research article that seems to have gotten lost in researchers' everyday analyses. She talks about modeling that comes from multilevel factor analysis, inspired by multilevel factor analysis. And she argues then that factors from cross-sectional analysis are partly determined by between and partly by within-person covariance structure, citing Cattell in 1978. And that really reflects this uninterpretable blend of within and between parts of a multi-level model that Raudenbusch and Breich have talked about in their 2002 book. Now, multi-level based longitudinal factor analysis allows for these differences between person and trait. There are trait-like factor structures, FB, and within person state-like factor structure, or FW, at the different time points. And it's sufficient actually to have only 2 time points, as in the picture we drew, to determine this within person factor structure. You don't need the intensive longitudinal data to estimate a factor model for each person, the so-called n=1 analysis, or Cattell's P technique. And this relates to latent state trait work, which has a lot of articles that emanated with the latest one in the series is Chris Geiser's 2020 book on longitudinal structure equation modeling from a latent state trait perspective. So now if you then take this longitudinal factor analysis based on multi-level thinking and have individual at the top level and time at the bottom level, we can add this path between the 2 time points, time point 1 and time point 2. So that's an autoregression for the FW factors, for the within factors. So that would correspond to a cross-sectional model that I talked about before, where students within school, 2 students within a school influence each other. So this multi-level based longitudinal model is quite different from the usual naive longitudinal model, which uses only the bottom part here, perhaps adding some correlated residuals across time where you would need them, but not in this disciplined fashion of having one set of random intercepts that have influence on all the outcomes at both time points.